Okay. So, we know from vector algebra that for two vectors P and Q, we can define a dot product as PQ cosine of theta. And, well, theta is the angle between the two vectors. So based on this definition, we can get a projection of a vector on a given axis. So if we have vector P and we have OL as the axis, then we can use this dot product to get the projection of this vector on OL. The only thing you need to do is to define this OL as a unit vector in that direction. So we write PQ, P dot Q over the magnitude of the Q. So here Q is the axis you want the projection on. And so we go forward, we have the triple product. And so if we have three vectors, we can define S dot P cross Q. And this would be representing the volume of the parallelepiped that these three vectors are forming. So this P cross Q would give you another vector perpendicular to the plane that P and Q lie. And the dot product would give you the volume. And so based on this definition, we can go to the physics of the problem and write the moment of a force about an axis with this triple product. And so this lambda here is the unit vector. And R cross F is the moment of the force about a particular point on this axis. So what you do is that you pick a point to calculate the moment about, like what you did before. So here we pick point O. And then calculate the cross product. It gives you the moment of this vector. And then if you simply make a dot product with the lambda of the vector, you get the projection of this cross product over the unit vector here. Any questions? You had this in your problem set. Okay, Jimmy, this triple product is actually the mathematical definition of the moment of a force about an axis. I guess you had a couple of problems in your homework number 4, which you must have submitted, right? And so let me. Yeah. So I'm going to solve. Go over an example here. No problem. And but the only important thing is practice, because it might be a little bit abstract to you. And the only thing you need to do is to solve a couple of problems, redo your homework problems, and that would be fine. But back to this triple product, as I said, this is a mathematical representation of the moment. So this R cross F would give you the moment about the point. And if you make a dot product, you're actually projecting that moment on a given axis. So that axis is represented by this unit vector lambda. So in this problem, Oh, okay. So, and let me see. Is where your projection, yeah, it's the unit vector of the given axis that you want the projection on. Oh yeah, so the projection and the given axis are actually in the same direction. Is that clear? Okay. So this triple product could be written as a determinant of these three sets of components. So in the first row, lambda component, second row, R component, and the third row, the force component. So as usual, you can always use the algebraic equations to write these, or you can use these determinants. There's no difference. You can do both in your exam or whatever. So in this problem, we have a 23-inch vertical rod, and we have a and this rod is actually welded to the midpoint C of this AB rod AB here. So we want the moment of force P about AB. So we want to form a triple product. So first you need to calculate R cross F, and this R cross F would give you a moment. So the cross product is a vector, so this moment would give you a vector. So this force would exert a moment about any point on this line AB. So I can pick any point here to calculate this R. So this R could be from the force that we want to exert the point, like G, I'm sorry, so this force it could start from B, or it could start from A and ends at any point on the line of action of the force. So it could be G or any point. So this P is passing through G, so we can pick G as the point, or we can pick D. So this R would be from B to D. Or A to D. Okay, is that clear? So you can pick any point on the line of action as you did when you wanted to calculate the moment of a force about the point, and then the point that you want to calculate the moment about could be any point on the given axis. So it could be A or B or any point between on this line AB. So then I can write this M. So all of these are equivalent. So in this problem, you can choose from B to G. Sorry, there's because we pick these two because in the Z coordinate, you don't have any displacement. So from B to G, the third component of this R would be 0. Any questions? Okay. So first we need to derive lambda AB, which is the unit vector along this axis AB. We calculate AB. Yeah, no problem. It could be any point on the given axis. We can mathematically prove that this triple product does not depend on the point that you choose as the reference point to calculate the moment and the point on the line of action of the force. So then we pick point G here, and then write R from B to G, and then we have to write the force in vector form. So we calculate the unit vector, which is dg bar over dg here, and write the force in vector form. And then we can use the determinant to calculate the moment of P about AB. So the procedure is like this. So you first determine the unit vector AB, which is the unit vector of the given axis. This is the axis that you want to calculate the moment about. So you pick 2 points, A and B. You calculate the displacement vector and the magnitude of the vector, and you derive the unit vector. In the second step, you apply force P on some point on the line of action. So here we pick point G. It could be any other point like D or any other point on this line of action from D to G. Again, you have to determine the unit vector of the force. So you write the displacement from D to G and then the magnitude, and then you calculate the unit vector. And then you can write the displacement vector from B to G. So I'm going to write here that at the end we want to calculate lambda cross R, lambda dot R cross F. So what we do is that we should identify each of these vectors. And then we can, for this triple product, we can write this determinant and calculate the moment. Is that clear? Any questions? No questions. Okay. Let's start a new topic here. So we want to see how we could derive equivalent system of forces in rigid bodies. And now you've learned how to calculate the moment of a force about a point, and of course you know the moment of a force about a given axis. These two are very important. And so if you have a system, so if you have a rigid body with multiple forces acting on it, then you simply calculate the moment of each force about a given point, let's say O, and then sum them to get the total moment. So there's another concept here, which is couple. So if you imagine that you have a bolt and you want to rotate this bolt with a wrench. Although you're exerting forces, but in statics you show this force by a moment, and we call this a couple. And the reason is that if you consider the bolt, then this wrench is actually exerting two forces. Equal but opposite in direction. So this is F, this is minus F. And this would be equivalent to just a moment, a couple. So that's why we extend our definition of total moment to this formula here, in which we simply add the couples and the moments of the forces about given point. So I'll go into more detail. So if we have a rigid body with three forces or any number of forces, then you can make an equivalent system so that the effect of these forces on the rigid body would be similar in both systems. So the rigid body, the shape is actually the same thing, but we can write the resultant of the forces and moment of the force about point O, and exert this R at the point that we calculate the moment about, and also exert this moment as a couple. So system A and system B are equivalent. We know from before that you are only able to move the forces on the line of action. But here, we are making an equivalent system. So mathematically and physically, it is correct to move all the forces to a single point and substitute them with the resultant and a couple. So for rigid bodies, it doesn't matter really whether you have multiple forces acting on the system or a single force and a moment at point O here or any point in the surface. Any questions? So this is a general rule. For rigid bodies, you can always do this. This moment is not the moment of this R about point O. So this MO is the moment of RF1 plus RF2 plus RF3. So let's say R3, R2, R1. So if this is point O, then we can draw a displacement vector and call this R2, then this is R1, and this is R3. So we are talking about the initial system. So sigma F would give you F1 plus F2 plus F3. This is the resultant force, and the moments are actually R1 cross F1, which give you M1, the moment of this single force. And you can calculate the total moment by just summing all the moments. So this M is not the moment of the resultant force, it's the moment of individual forces in system A. So when we go to system B, then we substitute with all the forces with this resultant force at point O and the moment at point O. Is that clear? So we can have another equivalent system. So from B we can go to C to eliminate this couple here. So we just move the resultant force from point O such that the distance from O to the line of action would be the magnitude of the moment over the magnitude of the force. So I can go the other way. If I have this system as my initial system and want to move force R to point O, what I should do, I should just calculate the resultant and the moment. So you have only one force here, which is R. So this is the resultant force, and the moment would be R. So would be dr. So these three systems are actually equivalent. Any questions? Okay. So let's solve an example to make things more clear. So if we have an I-shaped beam and exert a 260-pound force at point A, then what would be the equivalent force coupled system at center C? So we have an I-shaped beam and we can make an equivalent so we just so this is point C and this is point B and A, and what we do is that we calculate the resultant of the forces, which is 260 here. Well, this should of course be in vector form, but I'm writing everything briefly here so we can see the details in the next slide. And the moment, so the moment is R cross F. And then we replace this we substitute, we make the equivalent system at point C plus a moment. So I'm going to describe the solution, but for the next question, I give you some time to think about it. This is a, so you have to remind the definition of the moment. So if you have a force, the R would point from C. So this R is actually from C to any point on the line of action. So for example, it could be B, or it could be A, or any other point on the line of action. Clear? So it's not that complicated. You just need to calculate the moment first about the point. So here the point is given to you. So because we want to replace the force at point C, so we calculate the moment about point C. So it would be C to B or C to A, and so the force is 260 in direction AB. So what you need to do is to write this force in vector form. So you know the dimensions, you can derive sine and cosine. And then write the force in this form. So 2.5, this is the triangle we're looking at. And this is alpha. So sine of alpha, 2.5 over the hypothesis AB, cosine is 6 over the hypothesis. And then you can write f. So I remind you that you should always have some coordinate axis. Well, let me see what is the, yeah. And then you calculate the moment about point C. So you take 1 point on the line of action here, A is taken here, and then this is R. And you can simply get R is 2.5 in X direction and 4 in Y direction, and cross it with the force. So this way you would get the moment of this force about point C. So you don't have any other force in the system. So you can simply write this as the equivalent force coupled system. Any questions? Yeah. So what is D here? So D here is MC over F. And that would be the distance, the perpendicular distance from C to the line of action. So this D is I'm just writing the relation between these two triangles. So D over 2.5 would be 2 over AB. What was AB? 6.5. Oh, you don't need to do that. I'm just showing that these are equivalent. So D would be 5 over 6.5. Does it make sense? I don't think, no. It's not on this on the first midterm. Yeah, I guess the first midterm would be moment of the force about a point, and moment of the force about a given axis, and the rest of the rest of the materials that you learned. But not this equivalent force coupled system is not going to be there. Okay. Any questions? So let's go. We have about 10 minutes. So as a practice for your midterm, I give you some time to solve this problem. So we have a irregular component, and we have multiple forces acting on this component. So you have all the dimensions, and at some points you have the angles to calculate the sine and cosine for each force. And you have two couples, of course, at point F and H. And I remind you that the total moment is the total couples, and R1 F1 plus R2 F2, etc. So this is the total couples. So this machine component is to be held in place by a single rivet that can resist the force but not a couple. So for P0, determine the location of the rivet hole if it is to be located on line FG or on line GH. So give it some thought, and then we can go to the solution and check everything. And let me know if you have any questions. So first step, You have to determine the equivalent force coupled system. For that, you need to pick a point in space and calculate the moment about. So can anybody tell me what that point is? So what do we want? What does this question want from you? So it determines the location of the rivet hole. So this rivet hole is not supposed to bear any moment. So if you remember, we have initial system with forces, then we would go to another system with the resultant force and the moment, and then we would go to another system without any moment. This was the initial figure that we had. Like this. So we want to derive two equivalent system BC for this problem. So we know that in the third step, the point that this resultant force act on is the rivet hole, and that would either lie on line FG or on line GH. So it would tell us that for the second system, it's better to pick the point on the intersection of these two lines. So if I pick point G, and then in the second system, if I pick point G and calculate all the resultant force and moments, so I would get something like this. And when I want to go to the third system, I would simply move this force on line FG or on line GH. To eliminate the moments. So what you need to do for the first step is to calculate the moment and the force about point G. So let's go to the solution. Okay, the resultant force is equal to, in x direction, 200 times cosine 15 and minus 120 cosine. This is the 120 force plus P, and you would get this R, and you can write this for the y direction, and then you can calculate the moments. So we pick point G and then calculate the moment of each force. So the first term is the x component of this 200 force. The second one, the y component. Then for this 120, we have two forces. Because it's the two-dimensional problems, we avoid the cross product and simply write m as fd, such that this d would be the perpendicular distance to the point that we want to calculate the moment about. So I'm sure you're already familiar with this from your homeworks. And this is important because this would be part of your midterm exam for sure. If you get any two-dimensional case, you decompose the force in x and y components and calculate the moment like this. Okay, this is what you get for mg, and of course you have two couples at the end. So we have a question. No, I get to that point. That's why we pick point G. Just to clarify the signs, you can see that the clockwise moment is defined as negative and counterclockwise as positive. So we have two couples counterclockwise, so we get two positive couples, and this is important. So in two-dimensional cases, you assume that the counterclockwise would give you positive moments, and you then follow the instructions and calculate the moments. So it's just a convention. Okay. Now we know both the resultant and the moment at point G. So your question was why we picked this point G? Because at the end we want to put a rivet hole on line FG or GH. So if I pick another point and calculate the resultant and the moments, then in the third system, I have to make an equivalent system and translate this R to this point on line FG and on line GH, while I don't know where that point actually is, right? Because we know that this point does not bear any moment, but we don't know that. So it would be a little complicated. So if you just pick the intersection of these two lines and translate R to that point, So this is R. Then you can easily move this on the Y direction or in the X direction, and calculate this distance here. No, it's not the same. Well, you can calculate that, but it's not necessarily the same thing. As we were discussing, if you move this R to a point on line FG or GH, you can find a point that there's no moment about that point. So this is actually the whole point here. The moment about points in space are not the same, are not similar. Yeah, so some of the moments, because these are the two couples here. So this is a couple here at point H and couple at point F. These are external moments. These are not the moments that we calculated. So if you look at the problem, you can see that you have these two couples. It's like a wrench. So you imagine that you have a wrench here, and it is exerting a couple and without any force. So I refer you to your textbook and read about the couples if you're not familiar with that. Yeah, so it's like you have a wrench here and you have a bolt here, and this is the couple about that point without any force. Okay, so you just, if it is in this next section, if it is on line FG, then you just divide it and divide the moments by the total force. Of course, if it is on line FG, it's just the X component, so it is Rx. You simply divide it and get the distance, and this is of Ry. Well, we are out of time, so if there's no questions, because it is 0, P is 0 in this question. So in this example, as you can see, there's no P here. Question with the midterm, I don't know. I have no idea how many questions you have. No graphing calculator, but if you have trouble finding a suitable calculator, you can contact the professor and see his idea. No, it's not on midterm. This equivalent force couple system is not on midterm. And we are going to solve more problems on this issue in the next session. So is that clear? Extra problems you can, well, Beer-Johnson problems are all good. So I guess you can find some of them in the red color, which are more difficult. And if you find yourself comfortable with the easy questions, you can solve the red color questions. Um, I'll have a look at the textbook, and for this midterm, maybe a couple of questions would be good to solve, and I would email that to you. Any other questions? Okay, have a good day, everyone, and good luck with your exam.